Okay, so thank you very much to the organizers for the invitation to give this course, and especially to Kostya. I'm very happy to be here. So let me begin with very basic notions to fix terminology. Suppose that G is a topological group, and X is a topological space. So an action of G on X is a map from G times X to X with the property that for any little element, little g of the group, the map from X to X, sending a point to big phi of G comma X, is a homeomorphism. And such that the morphism, little phi from G to X, to the group of homeomorphisms of X, sending G to little phi G, is a homomorphism of groups. What I'm actually defining here is an action on the left, okay? Because I take the standard group structure on the homeomorphism group, on the set of homeomorphisms given by composition, okay? So this is a left action. And the standard notation is to write G dot X or sometimes Gx for phi of G comma X. Okay. Some more basic definitions. The stabilizer of a point in the space is the group of elements of G whose action on X doesn't move the point. Okay. Now a point is fixed by G if the stabilizer is the entire group G, and the fixed point set is the collection of fixed points. The action is said to be effective if the morphism little g is injective. Okay, and the action is said to be free if the stabilizer of each point is trivial. Okay, now we will be interested on smooth actions, and these make sense if G is a Lie group and X is a smooth manifold. And in that case, so if G is a Lie group and X is a manifold, the action is smooth provided big phi is a smooth map. And this implies that the morphism little phi sends G inside the group of diffeomorphisms. Okay, so these are the basic definitions, and what are the basic problems in the area of finite transformation groups. This I didn't specify. I will be interested in the case in which G is a finite group. So usually for us, G will be finite, and X will be a closed manifold. Now the basic problems, well, there are many problems one can consider. Can you read this? I don't know if I'm following a good strategy to erase and immediately write. Yeah, maybe I should erase everything and then come back here. Let's do that. Yeah, that's a good theorem. I don't need the proof. Well, I have it here. Sorry? Oh, yeah, that's fantastic. Yeah. Very good, very good. Okay, yeah, let's do that. Not with all of them. Is there something I need to press?
Well, I find out. Maybe this.
I see.
No, it's not.
No, this one isn't working. Well.
No, it doesn't work. Here?
It doesn't work. And this neither. Okay. Can I erase here? Just to make some time. Okay. Still wet. Let me write here meanwhile. Good. So for us, G will be a finite group, and X will be most of the times a closed manifold. Okay. So now, what are basic problems in the in the theory of finite transformation groups? Well, I mean, given G and X, we would like to understand the geometry of all possible actions of G on X. So this is a very common symbol to denote that G is acting on X. Okay? So for example, we would like to understand whether there exist free actions. Or do all actions have necessarily fixed points? A more ambitious problem is to classify all possible actions. And typically, we would like to obtain a classification up to diffeomorphism or even up to homeomorphism. Let's say up to diff to be concrete. And this up to diff means up to conjugation. So if you have two actions inducing morphisms phi and psi from G to the group of diffeomorphisms, they are related or are conjugate if there exists some diffeomorphism such that psi of G is phi of G conjugated by F, and this for all G. Okay, and let's say a third problem would be to understand, given a manifold, what are the finite groups that can act effectively on that manifold. Of course, if we remove the condition of being effective, then any group can act on any manifold in a trivial way. Okay? Well, so these questions, especially 2 and 3, are very, very difficult, and it is in general impossible to give a complete answer to them. There doesn't exist any machine that takes as input, say, a closed manifold and gives you back the list of finite groups acting on that manifold. But many things are known, and in low dimensions you can obtain very satisfactory answers. Let me talk about the cases of dimension 1 and 2. In dimension 1, let me put an exercise. So let me talk about low dimensions. So this is an exercise. If you have a smooth and effective action of a finite group on S1, prove that then there exists an embedding of G in the group O2R. Well, that's an easy exercise. And consequently, G is either cyclic or dihedral. In dimension 2, one has the following result. So suppose that sigma is a compact, connected and oriented surface of genus G. Or let me call the genus H and reserve G for the group. And suppose that G is a finite group acting on sigma smoothly and effectively. Then one can make the following statements. If the genus is 0, then there exists a subgroup of G such that its index in G is at most 2, and G can be let me be consistent. Can be embedded in the group PGL2C. G0, sorry, yes. If H is 1, then there exists a subgroup such that which has index at most 12 inside G, and this subgroup embeds in S1 times S1. Okay, so and finally, if H is bigger or equal. Sorry? Both. Sorry? Yes. Yes.
Well, it has actually some probability because we assume that the X.
And if H is bigger or equal than 2, then you can bound the cardinal of G by this formula. Okay. Let me prove this theorem. So the basic idea here is to take a G invariant Riemannian metric. You can do it as follows. Let G0 be any Riemannian metric on sigma, then you average G0 over the action of the group. Now that's a bad name, sorry. Let's call it zeta0. Okay. Well, you don't really need to divide, but it's nicer this way. Now, this is a G invariant Riemannian metric. On sigma. And now we take the conformal structure induced by zeta. And this defines a structure of Riemann surface on sigma. And G does not necessarily act by automorphisms on sigma, automorphisms of a Riemann surface, because some elements might reverse the orientation. Okay, but there is a, you can define a group G prime to be the group of elements preserving the orientation, and then G0 can be identified with a subgroup of the group of automorphisms of sigma, and now I look at sigma as a Riemann surface, of course. Okay, and now if H is equal to 0, then by Riemann's uniformization theorem, we know that is isomorphic to CP1, and the automorphism group of sigma is isomorphic to this group. Okay, so you just need to take G0 equal to G prime. If H is equal to 1, then again by the uniformization theorem, but now for genus 1 curves, this can be identified with a quotient of C by lattice. Okay, and now G prime acts on sigma, which is a torus, and it turns out that you can if you define G0 to be the group of elements in G prime which act trivially on say H1 of sigma, which can naturally be identified with lambda, then this has index at most 6. Okay, so here I'm using strongly the fact that G prime is finite. Okay, and this is an exercise. Okay. So the thing is that in general, if you consider the action of the group G prime on H1 of sigma, this gives an embedding of a morphism from G to SL to Z. Okay, and you have to prove that if you have a finite subgroup of SL to Z, then it has at most 6 elements. This is the exercise. Okay, and now, so the elements of G prime, the action of the elements of G prime lift to an action of an infinite group on C commuting with the action of lambda, hence given by translations, okay? And hence you get, if you pass to the quotient, you get an embedding of G0 in S1 times S1, okay? And finally, if H is bigger or equal than 2, then Hurwitz bound states that the automorphism group of sigma has at most 84 times H minus 1 elements. Okay, and now this gives a bound on the size of G prime, and this proves the remaining statement. Okay, so, well, this provides a, yes?
You write sigma is isomorphic to CP1, but if the Riemannian structure has not constant curvature, then
yes, but I have forgotten the metric. I only consider the conformal class. Okay? This means that in very concrete terms, you have a metric, zeta. Zeta, I agree, zeta need not have constant curvature, of course. Okay? But you can use the orientation of sigma and the metric to define a complex structure on each tangent space of sigma, given by rotation by 90 degrees. Okay, to define what rotation of 90 degrees means, you are using zeta. Okay, and you're using also the orientation, right? So this is the structure of Riemann surface that I consider.
it will be almost complex structure.
But in real dimension 2, all almost complex structures are integrable. So it is indeed a Riemann surface. Okay. Well, so my aim in these lectures will be to explain results that generalize to higher dimensions all these three cases. Okay. There will be a big overlap between the results I'm going to explain. So, for example, tomorrow I will give one result generalizing case 3, but I will give another one which generalizes both 2 and 3, and the third day I will give a result generalizing both case 1 and case 3. Okay. Well, let me see that I'm not forgetting anything. Yeah, okay. So the main tool I will use to study actions will be equivariant homology. And that's what I'm going to define now, but first let me erase this to prepare future blackboards. Can I erase this? So to define equivariant homology, one uses classifying spaces. Let me briefly recall the definition. So assume that G is a Lie group, for example, a finite group or S1 or whatever. A universal bundle for G is a principal G bundle such that the total space is contractible and the base has a structure of CW complex. Well, sometimes this second condition you don't ask, but for me it will make things easier. Okay, so is everybody familiar with the notion of principal bundle? I guess. So universal bundles exist and are unique up to homotopy. And well, I will prove the existence of universal bundles in all the cases that I will need. But let me claim that this is a very general fact, and it holds for more general groups than Lie groups, more general topological groups. Okay, so the reason it's called a universal bundle is that if you take any sub-CW complex X, you have a map from the set of homotopy classes of maps from X to BG, okay, to the principal G bundles over X up to isomorphism. Okay, and this is given by sending the class of a map F to the pullback of EG. And now the statement is that this map here is a bijection. Okay, so it's a very natural problem, given a space, to classify up to isomorphism all principal G bundles on that space, and here this gives us a translation of that problem into the problem of classifying the homotopy classes of maps from X to BG. Okay. Good. Let me prove the existence of the universal bundle for the case G equal S1. Okay? Well, by the way, the proof of this fact is not so hard. Typically what you do is you argue by induction on the skeleton of X, okay? And uniqueness follows, for example, from the fact that EG is contractible, okay? But also existence. Okay, so let's construct this universal bundle. We identify the sphere of dimension 2k minus 1 with the elements in CK satisfying this equation, okay? And you have an inclusion of S to k minus 1 inside S to k plus 1, sending an element to this one. Okay, and now you define S infinity to be the union of all odd-dimensional spheres using these inclusions. Okay, so we can identify these the elements of this space with the set of infinite sequences of complex numbers, so zeta I belongs to C, with the property that these sequences eventually vanish. So zeta I is 0 if I is big enough, okay, and you have, of course, the equation that the square norms of the elements sum up to 1. Okay, of course, this makes sense always because we're assuming that only a finite number of the z's are non-zero. Okay, so this is a set. We give the quotient topology, and in very concrete terms, this means the following. I think we should prepare backwards. Now, topology is, by definition, the following one. So you declare that some subset Z is closed if and only if its intersection with all finite dimensional spheres is closed. Then, okay, and that's for every k. Okay, so this is finite topology. Now I claim that this topological space is contractible. Okay. Well, let's take an element. In S infinity, this bold-face 1, and let me define a homotopy between the identity on S infinity and the map sending all points to this point here. Well, of course, I mean, what a bad student would do is to write this and happily conclude that you have the homotopy. But of course, this is wrong because so here I'm using the structure of vector space on C infinity. Okay, but this doesn't make sense because nothing prevents this expression from vanishing eventually. Okay, so if, for example, if x is minus 1 and t is equal to 1/2, this will be 0. Okay, and of course, if this worked, then you would conclude that all finite dimensional spheres are contractible, and of course they are not. But since we are in infinite dimensions, we can repair this idea and add the following term. And of course, we also want to add it on the Okay, so what is this sigma x? Sigma is a shift. Precisely because we have infinite coordinates, we can define a shift that sends each coordinate to the next position. Oh. This is dry. Oh. Okay, so this is the shift sigma, and now it is an easy exercise to prove that this never vanishes, okay? Using, of course, the fact that the elements in S infinity eventually become zero in all positions. So this ends the proof that S infinity is contractible. Now, S infinity carries a free action of S1. Okay, so this is a free action. And this action is defined as structure of principal bundle here. In fact, the quotient the orbit space can be identified with CP infinity, okay, which is constructed as a union of CPK for all k's using a very similar construction. So CPK is embedded in CPK plus 1. This way, and again, the topology is the limit topology. Okay. By the way, I didn't say it, but it is an interesting exercise to prove that this is indeed continuous. Okay, I specified carefully the topology in S infinity, and so you can check easily that this is indeed a continuous map. Okay. Now,
did we prove already the element that it's contractible?
yes.
So we did not make any complications to prove that this expression got met.
Well, I left it as an exercise. It's very easy. I mean, you given x, you consider the rightmost position, rightmost coordinate, which is non-zero. Okay, and of course, there is the danger that this is non-zero only when t is different from 0 or 1. Okay, so if t is different from 0 on 1, you look precisely at the biggest coordinate of x, which is non-zero, and then sigma x has a non-zero coordinate in the next position, which is not cancelled by neither of these terms, and this proves that this is non-zero. Okay. In fact, you can prove, it's a nice exercise to generalize these, for example, to construct universal bundles for all finite groups. It's not so hard. Okay, so now we have this projection. Well, I'm not consistent with the notation. Sorry. Let me write things this way. Better this way. Sorry. So this is a universal principal as one bundle. Okay, and well, I didn't write it down, but when you have a universal principal G bundle, you call the base of the bundle the classifying space. Okay. Okay. Now let's compute the cohomology of CP infinity. To compute the cohomology, I'm going to use the Giesen non-exact sequence. I guess everybody's familiar with Giesen? No? Let me just state the general fact, and you can look at the textbook for the proof. So if you have a principal as one bundle over a space X, then you can construct the following. You have the following sequence. You have a morphism from the kth cohomology of X to the cohomology of dimension k plus 2, and this is given by multiplication by the first-Chern class of P. Okay, so the first-Chern class of P is an element in the second cohomology group of X. Okay, and then you can pull back. So let's call pi the projection. You pull back this to the total space of P, okay? And then you integrate along the fibers, and I run out of space. So this is integration along the fibers, okay? So you lower the dimension 1 unit because this is the dimension of the fibers, okay? And now you can continue, okay? Now you multiply here by the first-Chern class of P, and you go to HK plus 3, and so on, okay? Now the statement is that this long sequence is exact, okay? So this is called the Giesen exact sequence, and you will find it in many textbooks in algebraic topology. It can be proved, for example, using the Thom isomorphism theorem for vector bundles. Okay, let's apply this fact to our situation. The thing is that we have the following so this is a piece of Gieson's exact sequence, and we know that S infinity is contractible. So assuming that K is bigger or equal than 1, this is 0, and this is 0. Okay, and we know that this morphism is multiplication by, let's give it a name, by T equal to the first string class of P. Okay? So, on the other hand, we know that CP infinity is connected. So, H0 of CP infinity can be identified with Z, okay? And this is true because S infinity is contractible, so are connected, and CP infinity is a quotient of C infinity, of S infinity. And we also know that CP infinity is simply connected. This follows from the homotopy long exact sequence. Okay, and this implies that H1 of CP infinity is trivial. Okay, so we know the cohomology in dimension 0 and 1, and we know by Gieson's sequence that the cohomology is periodic, has periodic of period 2. Okay, consequently, the cohomology, in fact, the cohomology ring of CP infinity can be identified with formal functions on T, okay, where T is this, okay, and of course it has degree 2. Good. Now I'm going to use this computation to compute the cohomology of the classifying space, but now for finite cyclic groups. Okay. In fact, I will only need the case of cyclic groups of prime order. The PBA prime. I will try to be consistent with the following notation. So mu p will denote the set of pth roots of unity. Yes?
How do you get power series there?
I mean, first recall that, you are asking about formal series or in general the fact that it is a polynomial on T?
I'm asking about formal series.
I mean, yeah, so cohomology is a product, okay, unlike homology, which is a direct sum, okay?
And what argument, C1 is the shared class.
Well, yeah, I mean, the Euler class or C.
Sorry?
Yeah, I mean.
How do you define it?
Yeah. You can associate to P a line bundle this way, and it's a complex line bundle, okay? And is that okay? You can also refer to it as the Euler class of the sphere bundle. How this is defined? Sorry?
I don't know how any of these are defined.
You can use, I mean, it would seem a circular argument, but one possibility, of course, is to pull back. Yeah, well, let me see. Maybe it's clearer. You can define it in several ways. For example, you can take a Czech representative of the first-chain class, taking a collection of local trivializations, okay, of P, right? So P is a principal S1 bundle, and this. Well, you will find it in many textbooks. I mean, if X is a manifold, yeah, you take a section and look at it. Yeah. Okay. Okay, so we would like to find the classifying space for mu p. Of course, as a group, this is isomorphic to Z mod p, but I prefer to reserve Z mod p to the coefficients ring and mu p for the group. Okay, so now I want to find the classifying space, and for that I need a contractible space on which mu p acts freely. But we do have such space because we know that S infinity is a contractible space on which S1 acts freely, and mu p is a subgroup of S1, so this works perfectly nice. Okay? Since mu p is a subgroup of S1, we can define we can take E mu p to be E as infinity. Sorry, what I'm writing. Sorry. So you take E mu p to be as infinity, and now you define B mu p to be the quotient of S infinity by mu p. Okay, and this is a universal mu p principal bundle. Sorry, principal mu p bundle. Okay. And erase. Okay. Now, my aim is to compute the cohomology of this space, right? Now, so we have the quotient of S infinity by S1, and we have called it B as1, it is a classifying space. And now we have the quotient to the classifying space of mu p. But then, of course, you have what's called a residual action. Okay, so here you have an action of S1 quotient by mu p. Okay, and now, of course, this group can be identified with S1. Okay, you simply consider the map from S1 to this to S1, raising each element to the pth power, and this descends to an isomorphism between this guy and this one. Okay. Right? So now this, the projection from B mu p to B S1 becomes a principal S1 bundle via this identification. Okay? Right? Okay, so if we know how to compute the first chain class of this bundle, then we will be able to apply Gisin's exact sequence and compute the cohomology of this guy. Okay? Claim the first chain class of B mu p is equal to p times the first chain class of S infinity as a bundle over BS1. Okay? So it's equal to p times t. Okay? But this is a very general fact. If you have a principal S1 bundle and you quotient each of the fibers by the nth roots of unity, you get a new circle bundle, and the first chain class, or the Euler class, has been multiplied by n. Okay, to prove the claim, I would need to rely on some particular definition of the first chain class, which I don't want. But let me say that this claim is equivalent to or roughly equivalent to the fact that the first chain class of the tensor product of two line bundles is the sum of the first chain classes of the bundles. Okay? So this is. Okay, if you use the definition of the first chain class in terms of a check cocycle, then it's a very easy exercise to prove this. Okay, you take local trivializations of your bundle, and then the structure of the bundle is encoded in the gluing maps. And then the thing is that the gluing maps are replaced by their pth powers. Okay, good. So now, once we know this, we have all necessary information to compute the cohomology of this guy. Concretely, let me see. Am I interested? No. Let me. Right. Let me do it with integer coefficients to begin with. So here you have So this is a portion of the Gisin's exact sequence. And what we know is that these are multiplication by t. And multiplication by t is an injective mapping in the cohomology of BS1. Consequently, you can ignore all this part here and insert a 0, okay? And now the conclusion is that the kth cohomology of B mu P is the following one. It's Z if K is equal 0. If it's Z mod P if K is bigger than 0 and it is even, and it's 0 if K is bigger than 0 and it is odd. You are right. Yes. Yeah. Which is still injective, but now the cokernels of these maps are either 0 or Z mod P, depending on the parity of K. Okay? And now, if you pass to Z mod P coefficients, the conclusion is that HK of B mu P is isomorphic to Z mod P in all dimensions. Okay. Oh, sorry. Okay, so this is an important formula which we are going to use a lot of times. Sorry? Yes, because now I have passed the coefficient in Z mod P. Okay? In fact, one can give an easy description of the ring structure of this cohomology, but it is a little bit more involved than the ring structure of BS1. Basically, you need one generator in dimension 1, then you take its Bochstein, which lies in dimension 2, and now this is the ring generated by the generator in dimension 1 and its Bochstein, quotient, of course, by the condition that the piece in degree 1 squared is equal to 0. Okay? But anyway, I'm not going to use this, so let me not write it down. Okay, so much for the classifying spaces. Let me now talk about equivariant cohomology. But first, let me erase this. Now we assume that G is a Lie group acting on a topological space X. Okay. Now the Borel construction is defined. It's not this way. And it's defined as the bundle associated to the universal bundle of G with fiber X. So this means the following. This means the product of E, G, and X quotient by an equivalence relation that identifies E, comma little x with g minus 1 of x. Okay, so here I'm following the standard convention that the action of g on a principal bundle is on the right. Okay, and all my actions on general spaces are on the left, and so this is consistent with this notation here. Right? Okay, so this has a structure. This is a fiber bundle over the classifying space BG, and this is simply induced by the projection from this product to EG. Okay, and this is the fibers. So this is the fibers of this vibration are X. Okay, so now the equivariant cohomology is defined, it is denoted this way. And it is the cohomology of the Borel construction, singular cohomology always. Huh? Okay. Okay. Let's consider two extreme situations. Suppose that first that G acts trivially on X. And this means, of course, that all points are fixed points. Okay. Then, so when you consider the Borel construction, you take this product and you quotient by this, but if the action of the group on X is trivial, then this G minus 1 disappears, and what you're simply doing is quotienting out by the action of G on EG. Okay. Okay. And consequently, you can compute the equivariant cohomology using Q-net formula. The other extreme is that in which the action is free. And then you can construct the quotient map from X to X mod G induces a vibration from the Borel construction to X mod G, okay, which is a fiber bundle with whose fibers can be identified with EG. But EG is contractible, so this is a homotope equivalence. In other words, if the action is free, then the equivariant cohomology is the usual cohomology of the quotient. Okay? And of course, so if X is a manifold, for example, so that its cohomology is located in finite dimensions, then the equivariant cohomology of a free action will also be a finitely generated module, whereas as soon as you have fixed points, the fact that you get this factor here, and as we know in the case in which G is equal as 1 or Z mod P, or sorry, mu P, that this is non-zero in infinite dimensions, then the conclusion is that these fixed points, the existence of fixed points implies that you have non-trivial equivariant cohomology in arbitrarily large dimensions, okay? So in general, what can we do to compute equivariant cohomology? Well, the Borel construction is a fiber bundle, so we can try to apply Serre's spectral sequence for this vibration, okay? But maybe I should erase Blackboard. Now we have a spectral sequence whose second page is this, and which converges to equivariant cohomology. Okay. I'm assuming that X, for example, has bounded cohomology. Okay, so this is a local system over BG given by the twisted product of EG and the cohomology of X. In particular, if the action of G on the cohomology is trivial, then you can replace this local system. The local system is trivial. Okay. Good. Okay. Let me now consider the case in which G is equal to Z mod P. And we have the following theorem. Suppose that mu P acts on X smoothly. So I'm implicitly assuming that X is a smooth manifold. Okay. Then, let me stress this one. This is a smooth manifold. The case equivariant cohomology of X, say with coefficients in Z mod P, is equal to the case equivariant cohomology of the fixed point set for any k bigger or equal than the dimension of x plus 1. Okay. Well, the idea of this statement is that if you consider an action of mu p, since the only subgroups of mu p are the total and the trivial subgroup, then in the complementary of the fixed point set, the action will be free. Okay. Let me see. Maybe it is a good point to give some technical result. Let zeta be a mu p invariant Riemannian metric on X. This exists by the same construction that I use in dimension 2. You take an arbitrary Riemannian metric and you average the, okay? Then for any point in X, the exponential map, for any fixed point, the exponential map with respect to Z at the point X is a map from the tangent space to X. Let us assume, for example, that X is closed or complete, or otherwise it will only be defined in a neighborhood of 0. Let's ignore this fact. The important thing is that this is a local diffeomorphism and it is equivariant. Okay? But I insist, I mean, it is only in general defined in a neighborhood of 0. Okay, so equivariant means the following. Sorry? No. In general, what I mean by that is that there is a neighborhood of 0, u, okay, such that the restriction of the exponential map to u gives a diffeomorphism between u and the image of u. Okay, which will be a neighborhood of X. Okay, where, sorry. So this is the induced linear action. Sorry? Well, let me write it down. I mean, I don't want to assume X to be closed in general. So this is going to be defined in general only in a neighborhood of 0. Okay? Okay. The thing is that once you have a point which is fixed by mu p, the action of the elements of mu p on the manifold induce an action by linear transformations on the tangent space at x. Okay? And this is equivariant. The consequence is that x mu p is a smooth submanifold of x. Okay, because locally on each point of the fixed point set, you can identify the fixed point set with the linear subspace of the tangent space at that point. Okay. Okay, so in particular, this means that, so here you have x, here you have x mu p, this is a nice submanifold, and you have a tubular neighborhood. Yeah, I think today I definitely can't speak more than beyond the hour, no, because you have to rush to take the boat. I mean, let me try to finish on time and we'll see. Okay, so you can construct a tubular neighborhood, let's call it U. Okay, so U is a tubular neighborhood of x mu p. V is the complementary of x mu p. And now the theorem follows from applying Mayer-Vietoris sequence for equivariant cohomology using this covering. Let me see. I'm going to try to finish. Oh, no, I didn't erase it. What I'm going to do now. Okay. Now, I'm going to use Mayer-Vietoris for H for equivariant cohomology and the covering of X given by U and V. Okay, so the equivariant cohomology is the cohomology of the Borel construction. Here I'm writing X as a union of two sets, and these two sets can be taken to be mu p invariant. Okay, certainly this is the case for the complementary of the fixed point set. This is preserved by the action of mu p, and if you define this tubular neighborhood precisely using an invariant metric like zeta, okay, then this tubular neighborhood will also be preserved by the action of mu p. Okay. This means that you can apply the Borel construction on both sides of this equality, and you get that the Borel construction of X is equal to the union of the Borel construction of U and the Borel construction of V, right? And now you apply the usual Mayer-Vietoris sequence to that union, and so in particular, what you have is the following. Let me write here also. Okay, and here H. Okay, so this is my Mayer-Vietoris sequence. Now, the key point is that the action on both on V and on U intersected with V are free. Okay, these actions are free, I insist because mu p doesn't have any non-trivial subgroup except from the identity. Okay? So this means that this equivariant cohomology, for example, is equal to the usual cohomology of the quotient by freeness of the action. Okay? And this is a manifold of the same dimension as M. So this vanishes if K, well, I should be a little bit careful. Let me put bigger or equal than the dimension of M plus 1 and, sorry, X plus 1. And maybe I should put a 2 here, but this is not too bad. Okay, I think so. And similarly, this vanishes, okay? Sorry, if K plus 1, sorry. For the same reason. Okay, and similarly, this piece vanishes, and now this is isomorphic to, sorry, I'm writing G instead of mu p. Okay, now the tubular neighborhood retracts onto the fixed point set, and this retraction can be obtained in a G equivariant way. So you get a homotopy equivalence between the Borel construction of U and the Borel construction of X of the fixed point set. Okay, and of course you have 0 here, and when you have 0 here and 0 here, this is an isomorphism. Okay. And this gives the desired statement. Okay, is that clear? Well, so it's time to stop. Next day, tomorrow, I will apply this to prove a theorem of existence of fixed points. Precisely, assuming that X is Z mod P acyclic, which means that it has in Z mod P coefficients the same cohomology as a point, I will prove that the fixed point set is non-empty, and in fact it is also Z mod P acyclic. Okay, and then using this theorem I will prove some restrictions on actions of finite groups on manifolds.